Again, dear colleagues, I want to present you the result of our work on the topic dynamic response of reinforcement concrete structure to an impulse localized impact. Currently, there is great scientific and technological progress in the development and creation of unique engineering and construction structures. These developments contain, as a rule, many new original engineering solutions, as well as use the latest advances in material sciences. On the one hand, such projects offer great prospects from the position of their functional use, but on the other hand, there is no experience of their long-term operation. An important factor is the high material value of such structures. It follows from these circumstances that the loss of bearing capacity of elements of these structures, violation of their integrity or destruction can lead to a situation of unsafe operation of structures, to large material losses, and even to human victims. One of the main means of ensure safe operation of unique engineering and construction structures is the development and use automated system of monitoring deformation processes, taking into account all individual features of the structure and its operation conditions. Today, one of the new and modern approaches in the design, creation, and implementation of systems of monitoring the stress-strain state of construction object is the use of system based on actuators. This is the object of this work. One of the significant aspects in the realization of this project is the development and introduction of method of diagnostic of the achieved deformation parameters using a system of actuators, which provide a specified external mechanical effect on the structural elements. During operation, the structure accumulated defects that introduce significant changes in the performance and can be diagnosed by means of vibration analysis of the evolution of the dynamic response. This is what actuators in the monitoring system are for. A vivid example of this is an example from the field of medicine. If we imagine that the building structure is a person who is a neurologist appointment, the example become even more clearly. The neurologist, as a prototype of monitoring system using actuators, can, by meaning of hammer and precise strokes on the nerve nodes of human body, characterize his condition and make a diagnosis, and guided by experience and statistic, make a prognosis. This is the purpose of creating such systems. In order to achieve the goals of the study, we need to solve a group of problems. These are presented on the slide. It's necessary to conduct a series of full-scale and computational experiments, which will form the basis of the developed monitoring system. Then, after creating such a system, it's necessary to verify it on a group of boundary value problems. So we began to investigate the indicated problems. On the territory of our institute, we designed and built a unique experimental stand for testing building structures. It's allowed to place on its construction objects or their parts of different scales. A monolithic reinforced concrete structure was built in this stand. Photos of stand and research object are shown on the slide. First, the strength problem of quasi-static loading of a part of the structure, which is presented on the slide, was solved numerically. The loading zone was selected, where the load, which in the process of increasing leads to the formation of a defect in the slab in the form of group of cracks, was realized. The problem has been solved in nonlinear formulation using William Wang model for modeling the behavior of concrete body of the building. According to the result of numerical experiment, the shape and magnitude of the defect depending on the level of loading have been established. Once the shape, dimension, and evolution of the defect under load have been established, the defect is embedded in the structure of the building. The crack distribution and dimensions of the defect zone are shown on the slide. Further, a series of problems on the analysis of the dynamic response of the structure to a given impulse action were also numerically solved. By means of modeling, an actuator was designed. The actuator diagram is shown on the slide. The type of signal from the actuator was selected, and the location of impulse load was also selected. The control points were selected on the structure itself in order to register the value of acceleration normal to surface of the structural elements. A series of computational experiments was performed where the pulse impact is first applied to the whole structure without a defect. The vibration portrait of the undisturbed structure of the object is taken and analyzed. This portrait is the base portrait. Then the defect of the given size and shape is gradually introduced into the structure. The implementation is carried out in stage. It's divided into 3 stages, 30, 60, and 100 of the crack height. At each stage, the vibration portrait of the structure is taken and analyzed, which corresponds to the given stage of the defect evolution. Then all vibration portraits are compared. The slide shows the result of the vibroacceleration analysis for point number 7, which is located directly above the defect growth zone on the opposite part of the floor slab. You can clearly see how the signal at the reference point changes as the defect evolves. If we consider the individual time intervals of the signal, the difference can be seen with the naked eye. The slide shows the time intervals of the signal, which clearly show the change in phase, amplitude, and even shape of the signal as the defect evolves in the reference area. All this suggests that the defect introduce quite tangible changes in the vibration portrait of the structure. Then, as a part of the signal compression, Fourier spectra were constructed for 2 parts of the entire signal, which was conventionally divided in half by time. If we compare the energy of the spectrum for frequencies intervals, it's also will seen that as the defect evolves, the energy of the spectrum also changed. This is especially well seen for the first half of the signal, when the signal reflections have not yet accumulated in the structure. It can be seen that the defect evolves for the frequency range of 4 or 5 kilohertz or 5 or 7 kilohertz. The spectrum energy decreases. The result obtained for the second part of the signal differ from first. Apparently, the reflected shapes have a significant influence. In any case, the significant change in the characteristic of the vibro portrait was recorded, which remains to be interpreted. We also constructed wavelet images for point number 7. The wavelet images are shown on the slide. They also clearly show the evolution of the signal as the defect grows. The next stage of the study is the full-scale implementation of prototype of the monitoring system with actuators at the site shown above. This work is in progress at the moment. In conclusion, I would like to note that the work is initial stage of research, but in our opinion, the results already show serious potential. There are still many challenges ahead. We will pay special attention to carry out full-scale experiments on the model or real building. Thank you for your attention.